Okay, it's my pleasure to introduce Ben Schulze, a fourth-year graduate student in environmental science and engineering at Caltech. Ben has done truly remarkable research on the nature and evolution of the Los Angeles atmosphere over the last 2 decades. And it's with great pride and pleasure that I introduce Ben to this distinguished audience. Take it over, Ben.
So thank you so much, John, for the very nice introduction. Good morning, everyone. Hopefully folks can hear me okay at this point. Please let me know if not. Today, I'll just give a brief overview of some of the work we've done in the Seinfeld group, trying to better understand the changing sources of ambient aerosol in Los Angeles. So if the slides will advance. Well, having a little bit of a technical difficulty advancing the slides here. Let me try stopping to share. Apologies. That seems to be working now. Apologies for the delay. So as the previous speakers introduced eloquently, atmospheric aerosol consists of suspended particulate matter produced from a variety of sources. We typically classify these sources as either primary or emissions directly in the particle phase. This is things like Saharan dust or sea spray aerosol, or secondary, formed from the oxidation of gaseous precursors. Just very briefly, as other speakers have introduced, these particles, especially in urban areas, are quite small. We're typically concerned with PM 2.5 or particles smaller than 2.5 microns in diameter. These particles are small enough that they easily navigate to the alveoli of the lungs and exert numerous negative cardiovascular and respiratory effects. And so the map at the bottom here is just an estimate of the fraction of annual mortality attributed to particulate matter exposure across the globe. And as you can see, it varies considerably depending on location, but in almost every one of the countries surveyed in this analysis, particulate matter exposure accounts for a non-trivial fraction of total mortality. Los Angeles has a particularly famous history of aerosol pollution, as some of the other speakers have noted. The image on the left is from an LA Times article in 1943 describing a plume of smoke that descended downtown and cut visibility to less than 3 blocks. Nowadays, we would refer to the smoke, obviously, as urban smog. Around that time, LA County established the Air Pollution Control District, and Ari Haagenschmidt famously began his experiments at Caltech focused on understanding the source of this smog. And Haagenschmidt was able to identify that nitrogen oxides reacting with hydrocarbons in the presence of sunlight produce both ozone, the primary gas phase component of smog, as well as aerosols. And since that time, work in John's group, as well as many of the others presenting today, have identified that historically in urban locations, on-road vehicles and industrial processes account for a considerable fraction of the total urban PM burden, and that these sources form aerosol through 3 sort of primary mechanisms. Inorganic components are formed, aerosol components are formed from the atmospheric oxidation of nitrogen oxides and sulfur oxide species and subsequent reaction with ammonia. Primary organic aerosol is produced. This is especially characteristic of things like diesel vehicles and the exhaust you might see at the tailpipe. And then secondary organic aerosol forming from, in particular, aromatic and alkane anthropogenic precursors, which are oxidized by OH, increase their functionality, reduce volatility, and then enable sort of partitioning of the particulate phase. So increasing interest in mitigating the air pollution problem has led to a suite of regulatory efforts over the last 50 to 60 years. I'm just showing a few examples of that here, things like catalytic converters, vehicle emission standards, new source performance standards for stationary sources. And those efforts have largely been successful. The figure, as we all know, the figure on the left shows the population of California, fuel usage in terms of gasoline and diesel, and GDP for the time frame available. And as one can easily see, all of these metrics have increased by more than a factor of 2 over that time frame. But as a result of successful sort of regulatory policies, concentrations of primary pollutants have declined consistently. So the top here is benzene, which everyone here will recognize as a toxic air pollutant in and of itself, and also a precursor to secondary organic aerosol. And NOx below that, a critical component for ozone formation, and also a precursor to inorganic aerosol formation. And as we would expect, the decreasing concentrations of primary pollutants has led to decreasing concentrations of secondary pollutants. So this is maximum 8-hour ozone concentrations at a variety of sites around Los Angeles, and as we see, sort of a consistent decline. While the historical record of continuous PM 2.5 measurements is shorter, for the sites where we do have data, from 2000 to 2010, we observed this rather steady, continuous decline in total mass loading by about a factor of 2 over that time frame. But if we look at the most recent decade, the progress has slowed considerably. And this is somewhat concerning, given that the current annual national ambient air quality standard for PM 2.5 is about 12 micrograms, suggesting that the LA region is sort of right on the boundary of what's considered safe by the EPA. And it's also puzzling, given that emissions from many of the precursors thought to be important for urban particulate matter formation have declined considerably over the last decade. So this is on-road reactive organic gases, which is analogous to VOC or SOA precursors on nitrogen oxides and sulfur oxides. And as you can see, these considerable declines in predicted emissions from the California Air Resources Board inventories have not translated into improvements in particulate matter mass loadings. And there's a few sort of primary hypotheses for why that might be. One is that organic components of the aerosol are accounting for an increasingly large fraction of the total as regulatory efforts have been implemented, and that due to effective regulation of the major historical sources, less controlled, what might be referred to as non-traditional organic aerosol sources are now quite important and not declining as rapidly. So the pie chart on the left is just a depiction of the contribution of individual aerosol components to the total measured in Pasadena on the Caltech campus in 2010. So organic aerosol is shown in green, and the various important inorganic components, nitrate, sulfate, ammonium, as the various other colors. And we see there that organic aerosol is already nearly 50% of the total that was measured in this field campaign. And if we were to remove some of the inorganic components that might be associated with sort of regional air masses and from a regulatory perspective would be difficult to control, organic aerosols maybe even more than 50% of the total. While we have relatively few measurements of sort of long-term organic carbon aerosol concentrations, the stationary monitor located in downtown Los Angeles suggests that organic carbon mass loadings have not appreciably declined over the last decade. And as we showed on the previous slide, this is despite the fact that the emissions from on-road vehicles have been reduced considerably. So this potentially suggests that there are additional sources of organic aerosol that now may account for a considerable fraction of the total. This would agree with relatively recent regional model simulations of organic aerosol in California and Los Angeles specifically. So the figures here show predicted 24-hour average organic aerosol mass loading simulated by a regional model compared with measurements at cities around California and in Pasadena specifically. And in both cases, as you can see for this relatively recent simulation, the model fails to reproduce the measurements consistently. And this is despite the fact that there's been impressive ongoing work to improve regional model representation of vehicular emissions, both in terms of the magnitude, the speciation, and their propensity to form secondary organic aerosol. And ultimately, it suggests that perhaps there are missing sources that aren't included in these models. And a few major categories of sources have been recently recognized, perhaps the most famous of which are what's referred to as volatile chemical products. So these are things like paints and coatings, cleaning products, and personal care products that historically weren't recognized as major contributors to the aerosol burden in urban areas, but due to the effective regulation of other sources are becoming increasingly important. And so the figure in sort of the middle there shows the per capita emissions of different categories produced from an analysis from Havila Pai's group at the EPA. And on the right is an estimate of the total per capita emissions in the US. As you can see there, it's on the order of 9 to 10 kilograms per person per year of these VCP emissions. So in dense urban areas, this could potentially be an important source of air pollution. A sort of now famous inventory analysis produced by Brian McDonald and the folks at NOAA demonstrated that while volatile chemical products account for a small fraction of the total hydrocarbon feedstock used anthropogenically within the Los Angeles basin, because of their large emission factors and propensity to form secondary organic aerosol, they account for, in this estimate, potentially more than 50% of the total SOA formation potential in Los Angeles. So the increasing relevance of VCPs may be a contributing factor in this sort of recent stagnation in the aerosol burden. Drew Gentner's group at Yale recently also identified that asphalt also acts as a considerable potential source of organic aerosol in urban environments. The figure shown here is the emission factor of various species as a function of carbon number and composition from asphalt at in-use temperatures, so 60 degrees Celsius here, characteristic of potentially like a summer day where sunlight is shining on the asphalt. And as you can see, asphalt largely emits species from about C12 to C18, or intermediate volatility organic compounds as they're referred to, which form SOA efficiently. And as anyone who's driven past a road paving operation can attest to, these emissions are quite a bit larger during the application stage, and decay relatively rapidly. But over the course of 3 days in the experiments performed by this group, the emissions never decayed fully, suggesting that the large amount of asphalt present in a large urban area like Los Angeles may act as a continuous source of organic aerosol. And an inventory analysis performed by their group suggested that the total source may be equivalent to on-road vehicles. There's a second potential mechanism that could partially explain the recent stagnation in air quality, and that's essentially that effective regulation of NOx emissions from on-road and stationary sources has led to an increase in the concentration of the hydroxyl radical in the Los Angeles atmosphere. So as previous speakers introduced, the hydroxyl radical is critical in conversion of both VOCs and inorganic gases to secondary aerosol components. And it's previously been observed in Los Angeles that on weekends, as a result of reduced commercial diesel traffic, heavy-duty diesel trucks, NOx emissions decline considerably. And as a result of the photochemistry involved in OH formation, this results in increases in OH concentrations. And this has been observed through sort of two analysis techniques. The first is observation of ratios of reactive aromatic species and alkane species with carbon monoxide. So one could imagine that over an urban basin such as Los Angeles, the various combustion sources produce aromatic species as well as carbon monoxide at some characteristic emission ratio, as shown in the schematic here. But by the time these species are measured, either from aircraft or at a stationary monitoring site, atmospheric processing of the reactive aromatic, which occurs much more rapidly than CO, has caused the ratio to decline. And one could expect that if the same measurement location was sampled during a period of higher OH concentrations, this ratio would be even lower. And that's exactly what was observed from aircraft measurements during the CalNex-2010 campaign from the folks at NOAA. So what this plot is showing is that the ratio of C8 aromatics to CO declines on weekends in red, despite the fact that the measurement location was unchanged. And their analysis suggested that there was a 60 to 70% increase in OH on the weekends in 2010. There were also direct measurements of OH concentrations during the CalNex-2010 campaign, which suggested that concentrations increased by 20 to 30% on the weekends. So both of these analysis sort of techniques indicate that the reduced NOx emissions on the weekends historically resulted in increased hydroxyl radical concentrations. So this is relevant because, as I discussed a bit previously, NOx emissions have been declining over the last 10 years. This is an estimate of weekday emissions in LA County from 2010 to 2020. And if we look at estimates of weekend emissions in 2010, those are likely comparable to current weekday emissions, suggesting that the same phenomena that produced the weekend effect previously may have induced this continuous increase in OH concentrations over time. And that would be expected to potentially increase the amount of SOA formed in the urban basin relative to a specific amount of organic aerosol precursors prior to advection of the air mass out of the air basin. So we were interested in trying to understand, in response to these sort of hypotheses and the observation of the stagnant PM mass loadings, what are the major sources of organic aerosol and inorganic aerosol to the extent that we can quantify them, and how have they changed over time, specifically over the last 10 years? How relevant are these recently recognized non-traditional sources of organic aerosol, and what effect has this changing OH potentially had on OA formation? So to answer those questions, we use data, a combination of data, ambient data, and detailed modeling of organic and inorganic aerosol formation And we obtained ambient measurement data from two campaigns that occurred a decade apart in the same location on the Caltech campus in Pasadena, CalNex-2010 and the Los Angeles Air Quality Campaign of 2020. And we used data from these campaigns because of the decadal timescale and because a relatively comprehensive suite of gas phase and aerosol phase instrumentation was deployed, enabling this source apportionment. So I'm primarily going to discuss measurements made with a high resolution time of flight aerosol mass spectrometer introduced by some of the previous speakers. It's a relatively unique instrument in that we can obtain chemically speciated, highly time resolved measurements of aerosol composition, whereas a typical stationary monitor located in the city might obtain one measurement every 24 hours. So operation of this instrument allows us to obtain data that looks like what I'm showing above in the time series here. This is mass loading as a function of time of organics and various inorganic components in 2010 from mid-May to mid-June. In 2020, we deployed the same instrument for a longer time period, but we sampled the same time of year such that we can compare the data sets and essentially attempt to understand how the sources of both the organic and the inorganic aerosol may have changed. When we do that, we produce the diurnal profile shown here. So this is the median mass loading of each of the major chemical constituents across a median day. So 12 is 12 noon their local time. And the sort of astute observer will notice quickly that over the last 10 years, there has apparently been a remarkable reduction in the mass loading of these nitrate and ammonium components. So we were interested in understanding whether the emissions reductions of nitrogen oxides and potentially ammonia that have occurred over the last 10 years could explain this trend. And sort of as I previously introduced, ammonium nitrate is largely formed from these emissions of NOx that are oxidized, either photochemically or at night. So if we look at the inventory data, again from the California Air Resources Board, the majority of this NOx emission reduction, of which sort of there's been a total of about 40%, a majority of that reduction has occurred due to improvements in on-road vehicle emissions. So to try and understand whether this magnitude of NOx emissions reductions could produce the change in nitrate aerosol that we observed, we developed a zero-dimensional model of overnight inorganic and organic nitrate formation, following the observation that during the CalNex-2010 campaign, we see this clear increase in nitrate aerosol overnight from about sunset to 6 a.m. So I won't go into the details of the model extensively, but essentially we model the relevant chemistry and physical processes involved in the formation of N2O5 and hydrolysis to nitric acid and uptake, as well as formation of organic aerosol production overnight. And we directly simulate nitrogen oxide emissions. We initially tuned the model to reproduce conditions observed in 2010, and we then iteratively reduce NOx emissions to assess the impact on nitrate aerosol formation. And essentially when we do that, we obtain the results shown here. And so this is modeled overnight production of nitrate aerosol as a function of the NOx emission reduction relative to 2010. And as we can see, we predict a considerable reduction over the last 10 years of about 70% or so. This is slightly less than the amount that we actually observe, but considerable nonetheless. And our model suggests that this is primarily the result of reduced on-road NOx emissions, with some benefits from emissions from other sources and co-benefits involving sulfate and organic aerosol production. We also predict this interesting shift in the composition of the nitrate aerosol from inorganic, predominantly inorganic in 2010 to half and half organic and organic, or even predominantly organic now. And this too agrees with some of our AMS measurements of nitrate composition. So ultimately, this suggests that regulatory efforts aimed at limiting NOx emissions from on-road vehicles have successfully reduced the production of an inorganic aerosol component in light ammonium nitrate. So if we return to our diurnal profiles, we see that the inorganic component has been reduced considerably as a result of this process, but we've seen less reduction in the organic aerosol, such that the organic now accounts for an increasingly large fraction of the total. Perhaps it's clearer here that there's been less change in the organic aerosol than we saw previously for the nitrate species, despite the fact, again, that there's been these considerable emissions reductions from the on-road vehicles. So to try and understand the sources of both the sources of the organic aerosol and why they how they may have changed over the last decade, we performed a combination of factor analysis using a technique known as positive matrix factorization and detailed modeling of the organic aerosol components. So very briefly, we lost connection. Can someone confirm that you can still hear me? I think we may have lost connection there for a moment.
It all seems good from this end, I think.
Okay, perfect. Sorry about that. So we first perform positive matrix factorization to essentially isolate locally formed aerosol from predominantly anthropogenic precursors from regional or background components that are relevant from a health perspective, but difficult to control from a regulatory perspective. And so the results of that are shown here for the 2010 data. We essentially observe individual organic aerosol factors related to urban secondary organic aerosol production, primary organic aerosol production from things like combustion processes, and a factor related to, or that seems to be linked to cooking related sources, and this background factor. So for the data from both campaigns, we remove the contribution of these background sources and label this anthropogenic urban OA. We then develop a model to try and reproduce this anthropogenic OA and determine what insights we can gain about how the sources have shifted over time. So again, very briefly, this model is a zero-dimensional model. It's essentially a quite simplified version of the types of models that John's group and John specifically developed years ago. And we essentially use emissions inventory data for individual organic aerosol precursors, things like on-road vehicles, off-road vehicles, the volatile chemical products I discussed previously, asphalt, cooking sources, etc. We use VOC measurements on campus to obtain estimates of photochemical aging timescales, essentially a metric for how much OH exposure the air mass was subject to prior to our measurement of them, and state of the science parameterizations of emission volatility and SOA formation. And this is essentially meant to capture the conversion of primary organic aerosol and gaseous precursors emitted within the urban core into this anthropogenic urban OA prior to our measurement in Pasadena. And so when we compile that information in our model, we produce the results shown below for the 2010 and 2020 campaigns. And essentially what these plots are showing is the mass loading of the measured sum of those PMF factors that I described previously in green, and the sum of our model components shown as the black trace there. We can quickly see that the model does a reasonably good job of reproducing the observed anthropogenic urban OA, especially in the diurnal average when considering the measurement uncertainty. However, the model suggests that on-road sources actually account for a relatively small component of the total organic aerosol in Los Angeles. 20% or so in 2010 and around 10% or less in 2020. If we look more specifically at the contribution of individual types of sources to this anthropogenic urban OA in 2020, and we see again that these on-road sources are maybe 10 to 15%, non-road mobile sources, so the total contribution from mobile sources are less than 40% or so, and that these area and stationary sources now account for the majority. And we can see that the largest individual contribution is from these volatile chemical products. The different bars here just represent different sensitivity simulations. So essentially this helps potentially explain part of this stagnation in local PM 2.5 mass loadings. As we've seen, on-road emissions of organic aerosol precursors from on-road sources have been reduced considerably over the last decade, but the available data suggests that these area and stationary sources in particular have undergone comparably smaller emissions reductions. We can also use the model to try and assess what effect any changes in hydroxyl radical concentrations have had on organic aerosol production specifically. So we don't have measurements of OH in 2020 during the Los Angeles air quality campaign, but we can infer OH exposure, as I introduced previously, from essentially ratios of volatile organic compounds. And so that analysis takes advantage of the fact that different aromatic species react at considerably different rates with the hydroxyl radical, as those here will know. And such that if we know the emission ratio of two species that react at remarkably different rates, so here being benzene and trimethylbenzene, if we know their emission ratio and we measure their ratio in the ambient atmosphere, in the afternoon in particular, we can infer the amount of OH exposure that has hypothetically occurred to produce the ratio. When we do that for the afternoon measurements in both campaigns, we see that the inferred OH exposure increased by about 50 to 60% from 2010 to 2020. And we can confirm with some modeling of air mass transport pathways that this isn't predominantly a result of changes in essentially the advection timescale, but really does appear to be increases in OH concentrations. And this change in OH exposure over time aligns with our expectations based on the NOx dependence. As we see here, OH exposure estimates display an inverse relationship with nitric oxide concentrations, the sort of dominant component of NOx emissions, shown in gray for CalNex-2010 data and in blue for the 2020 data. So ultimately, this suggests that, as expected based on theory, the reduction in NOx emissions over time has led to this increase in OH concentrations. We can then incorporate either the 2010 or the 2020 inferred OH exposure estimates into our model to assess what impact temporal changes in OH might have had on local organic aerosol production. So the figure here shows the diurnal average anthropogenic urban OA simulated by our model in 2010 in the sort of base simulation, in 2020 using the base simulation. So this is using estimates of OH exposure derived from the 2020 measurements, and then a separate 2020 simulation wherein we use OH exposure estimates from the CalNex-2010 campaign. As we can see, there's a considerable reduction in the simulated amount of anthropogenic urban organic aerosol. Stated differently, this essentially corresponds to about a 50% increase in predicted organic aerosol resulting from this inferred temporal change in OH concentrations. So again, this points to a second mechanism that may be contributing to the lack of improvement in recent air quality, as effective regulations of an individual pollutant have led to this unintended effect that increases aerosol formation rates from organic sources. So just to summarize here, despite the historical progress in mitigating Los Angeles air pollution, particulate matter mass loadings have remained relatively constant in Los Angeles over the last decade. And comparison of aerosol mass spectrometer measurements in 2010 and 2020 suggests that there's been a considerable change in inorganic aerosol, but only a minor change in the organic component. And we developed a model of this overnight nitrate production and specifically the ammonium nitrate. And our model suggests that there's been a major reduction in ammonium nitrate formation since 2010, primarily driven by reductions in on-road NOx emissions. As a result of that reduced inorganic aerosol formation, it appears that organic aerosol now accounts for a larger fraction of the total particulate matter burden, and that these less controlled, historically sort of non-traditional, non-mobile sources may now dominate OA production in the basin. And the available evidence suggests that increases in OH concentrations over the last decade may have offset emissions reductions that have occurred in terms of organic aerosol formation. So overall, this suggests that we likely need increased focus on these non-mobile area sources of organic aerosol precursors to achieve future air quality goals in Los Angeles. And we expect that conditions are somewhat similar in other major US urban areas, but that would certainly be an area for future research. So just to wrap up here, I'd like to acknowledge both John, of course, and the Seinfeld and Paul Wenberg research groups who were instrumental in this work, our collaborators during the Los Angeles Air Quality Campaign in 2020 at the University of California, Riverside and Irvine, and our various funding sources, including, of course, the Dreyfus Foundation. So I appreciate everyone's time, and if there's time, I would be happy to take any questions.